Today we will solve the problem 7.4 of Griffith third edition Introduction to Quantum Mechanics. The problem 7.4 is consists of three parts. We will solve one by one. First one is apply the perturbation theory to the most general two-level system. In the unperturbed Hamiltonian is that is H naught is equal to E sub A 0 and EP sub A 0. So you know this eigenvalue is a diagonal element. So this is for particle A unperturbed condition. This is for particle B unperturbed condition. And the perturbation is H prime is equal to lambda times this matrix 2 by 2 matrix. That is VAA, VAB, VPA, VBP. You know the meaning of this. So here VPA is equal to complex conjugate of VAB, that is VAB star. VAA and VBB are real, so that H is a Hermitian. Now the section A is find the exact energies of this two level system. So first we are going to solve this one. As given in the problem, the unperturbed Hamiltonian is equal to E sub A 0, 0 and 0, 0 E sub B 0, 0. That is, these two are unperturbed energy state. And H prime is equal to lambda VAA, VAB, VBA, VBB. Now, the total Hamiltonian H is equal to the addition of both, that is unperturbed Hamiltonian plus this perturbed Hamiltonian. So if you add these two, then you will get E sub A 0 plus lambda. Here you have lambda scaling factor lambda VAA, and if you add these two, you have lambda VAP, and here you will have lambda VBA. Then here you have E sub B 0 plus lambda VPB. So now I can take this as A, this parameter as A for mathematical simplicity, and I'll take this as B. So I can rewrite this matrix as A lambda VAP and lambda PA P, capital P. So now you use the characteristic equation to solve the energy level. That is a characteristic equation, you know, that characteristic equation is H minus lambda is eigenvalue, energy eigenvalue multiplied by unit matrix. So that is a diagonal element, you have to subtract by the energy value, e power minus a power minus e, here p power minus e. If you find the determinant of this, you will get a minus e multiplied by p minus e, and these two term minus lambda ABPA, because ABPA are complex conjugate. This can be written as minus lambda squared modulus square of VAB, which is equal to 0. Here in the characteristic equation, this will be equal to 0. Now you multiply these two. Minus e will become e square. I will form a quadratic equation. Then you take minus e outside. Then you have to multiply this minus e with p and this minus e with a. So this will become minus e a plus p. Then if you multiply a and p, you will get ab, and this last term I am keeping as it is. And now we will solve this quadratic equation. Now we have formed the quadratic equation. Here the coefficient of e squared is equal to a, which is equal to 1. Similarly, the coefficient of e is minus a plus p, which is called p. P is equal to minus a plus p. Then rest of the thing, these two things are called C. We will take this as C. So now the solution for quadratic equation is small c, remember that. E is equal to minus p plus or minus square root of p squared minus 4ac over 2a. Now, what is 2a? 2a is equal to 1. So this denominator simply pick up 2. So I can take it out 1 over 2. And what is minus p? P is minus a plus p. So this will become plus a plus p. And the square root of p squared. P squared is a plus p whole square minus 4ac. A is 1 and c is this parameter. That is ab minus lambda squared modulus vap square. So you can now you can simplify this. This can be what is the this can be rewritten as a plus p whole squared minus 4ab. Minus of minus will become plus 4 lambda square modulus vap square. Now you take this. What is this? You know very well that I can write here a squared plus, sorry, not a squared, a plus p whole square. That is a plus p whole square equal to m sorry, a plus p whole square minus here 4ab minus 4ab will equal to a minus p square. So I can rewrite this as a minus p square and this 4 lambda squared modulus vab squared. So this is the energy. For positive energy E plus, this will be plus. For negative energy, sorry, E sub minus. There are two energy level. When E sub minus, you use the negative sign here. So you can find this energy state E plus as well as E minus by substituting. We have seen that from the harmonic oscillator, sorry, not harmonic oscillator, from the Hermitian matrix, A is equal to E sub A0 plus lambda VAA, and P we have seen just now is equal to E P0 plus lambda VBB. You substitute this in the quadratic equation, then you can find the fourth energy state, the energy level, that is E sub plus as well as E sub minus. Then we will move on to next session. Now section P is you expand your result from A to the second order in lambda and then set lambda to 1. So now we have seen that E sub plus or minus is equal to half A plus P plus or minus this square root term. Now what I am going to do is I am going to take this outside the square root. So this will become just A minus P. So since we are multiplying this by A minus P whole square, then you have to divide the second term by A minus P whole square. So this will become like this. Then this square root of 1 plus this, let us say 1 plus some lambda square divided by x square can be written as this square root term can be approximately written as 1 plus of this term. So now this 2 will get cancelled with this 4. This will become 2. So now you can write E sub plus or minus is equal to 1 over 2 A plus P plus or minus A minus P, because I am multiplying this by 1. So A minus P plus A minus P, this term, that is 2 times lambda squared modulus VAP whole squared divided by a minus b whole squared. So now we will simplify this further. And now we got this expression. Here in the second term of square bracket, we can cancel a minus b with this a minus b whole square. This will simply become a minus b. Now we know a is equal to e sub a0 plus lambda VAA. Similarly, p is equal to e sub p0 plus lambda VBB. You substitute it here for a plus b. So this and this, if you add this, you will get a sub a0 plus e sub b0 plus lambda VAA, this VAA plus VBB. Similarly, here you have A minus B. This will become EA0 minus EB0 plus lambda VAA minus VBB. Plus this can be A minus B can be approximately written as because it is in the denominator, you can write this as EA0 minus EB0. You can ignore this VAA minus VBB term. It is approximately equal to this one. Now you use the plus, E plus. What is E plus? You have to add these two. So when you add this green color term, EA0, EA0, you have 2EA0. Similarly, what will happen to EB0? Here minus EB0. So that will get cancelled. And about this, here you can see VBB, lambda VBB will get cancelled with lambda minus lambda VBB. So you will get 2 times VAA. I am assuming here lambda is 1. So that you will get here 2 V modulus VAB squared divided by EA0 minus EP0, which is equal to, here you have an half. So this will get cancelled with 2, square root 2 here, here square root 2, here square root 2, here 2, here 2, and here 2. So this can be written as EA0 plus VAA plus modulus VAB whole square divided by EA0 minus EB0. So similarly, you can get E sub minus is equal to, instead of A, you will get B. EB0, you adopt the same technique, plus VBB minus modulus VAB squared divided by E sub A0 minus E sub B0. Now we got E plus is equal to EA0 plus VAA plus modulus VAB squared divided by EA0 minus EB0. Similarly, E minus, here plus will become minus, and A is will become P. EB0 plus VBB minus this one. So, what is the first order energy correction? By definition, the first order energy correction is the expectation value of perturbed Hamiltonian in an unperturbed energy state. That is psi sub A0. Psi sub A0. This is unperturbed wave function. So, this is the vector is row vector, row matrix. So this is A is 1, P is 0, because we are dealing with psi A only. And then the H prime matrix is VAA, VAB, VBA, VBB. And what is this is column matrix. So this is for matrix psi A. A is 1, P is equal to 0. Now you multiply this row and this first this row and first column, which you will get VAA, and this row and second column you will get VAB. Then again you have to multiply by 1 0. Now if you multiply by this 1 0, this is row matrix and column matrix, you will get VAA. This is the first order energy correction, that is this term. Then for VB1 first order correction, in similar manner, if you do this same thing, you will get VBB as a first order energy correction of wave function P. So this one. So naturally the second order wave correction is the third term here and here. We will do it in a formal way. We know by definition the second order energy correction E sub A2 is equal to the modulus square of the inner product of psi p0 h prime psi a0 psi a0. So we have to take modulus square. Then what is this product numerator? That is inner product of psi p0 h prime psi a0. So here you can remember psi a is missing here. So psi a is 0. This is the row matrix. Bra vector is a row matrix. So 0 and you have P is 1. Then the H prime matrix, and this is row matrix. This will become, this is for A. A is first row, so 1, and P is second row, that is 0. You do the same thing. If you multiply 0, 1, this, you will get PA1. So if you carry out like this, you will get VP. So what is modulus square of this one? Modulus square of this one is modulus AB square divided by EA0 minus EB0. You adopt the same technique for VB the 2, that is second order energy correction of P. So which is equal to, if you do the same thing, you will get minus modulus VAB squared divided by E sub A0 minus E sub P 0. That is in EA2, second order correction is this one. Exactly we got. Second order correction for the wave function P is this one. Of course with the negative sign. So we have found the second order energy correction, assuming that lambda is equal to 1. Then we will move on further. Section C is setting VAA is equal to VBB is equal to 0, so that the series in P only converges if modulus VAP divided by EB0 minus A0 is less than half. We have to prove this. If VA and VAA VBB P is equal to 0, then E sub plus or minus will become half EA0 plus EB0 plus or minus, because we are making VAA VBB zeros. Then EA0 minus EB0 square root of 1 plus 4 modulus VAB square divided by EA0 minus EB0 whole square. Now in order to have a convergence, this modulus of this term must be less than 1. That is, this must be negative, modulus of this. So modulus of 4 VAB square divided by EA0 minus EB0 whole square is less than 1. Now if you take square root, this 4 will become 2. Then if you take 2 the other side, this will become 1 over 2. And VAB, this will become VAB squared will become VAB, and this square get removed because we are taking square root. So this will become EA0 minus EB0. In the given problem, it is EB0 minus EA0. Since you are taking modulus of this, the change of order does not affect your result. If you bring this EA first, maybe this may be the negative, but if you take modulus of this, you will get the same value. So this must be less than half. So hence we have proved the section C also. So thank you very much for watching my video and supporting me continuously. Thank you very much.